So weak lensing is one of our most powerful cosmological observables. It has immense potential to probe the expansion history of the universe, to map dark matter concentrations, and beyond testing our standard model, it can be used as a tool for investigating galaxy formation at small scales. Now, that's all great on paper, but in practice, weak lensing data is a little tricky to work with. Now, the field has rapidly changed. I did my first weak lensing project just less than a decade ago, and there was buzz at the time because this groundbreaking experiment called CFHT lens had just measured weak lensing from 9 million galaxies, and they constrained cosmological parameters for the first time with cosmic shear, and they found something slightly different to Planck CMB. Now, it's very different now. Weak lensers are being fire hosed with new data. There's no polite way to put it. In the last decade, we've had the Dark Energy Survey, the Hyper Supreme CAM survey, and the ESO Kilo Degree survey. And in the coming one, we'll have Vera Rubin, Euclid Space Telescope, and Nancy Grace Roman Space Telescope. And that means the game has totally changed. So our task is to attain a thorough understanding of the challenges that face weak lensing and photometric surveys, and to be able to have complete control over our systematics. We have to make sure that our systematic error budget doesn't overpower our statistical power that we're about to get. And so we need to be creative in building novel methods. And I want to be careful when I say that because, you know, it's exciting that we have new methods or high order statistics that we can say improve our cosmological constraints by a factor of 2 or 3. But really much more crucial than that is that we need novel methods that can ensure accuracy of what we're getting. We don't have to worry about gaining in precision. We get that already. And so we need to make sure that we are accurate and that we are robust to the systematics in the data and in the model. So mostly since my PhD, I spent my time working as part of these large surveys and leading these large surveys to build and calibrate weak lensing data and release that to the public to enable a wide range of science. And in our surveys, our key project, our deliverable is to test lambda CDM, the standard cosmological model, with dark energy constraints. That's what we promised the Department of Energy. And so weak lensing is at the heart of the science questions that drive my research. So does the standard model, does it work? And more specifically, you'll see I'm focusing on, does the standard model accurately describe the nonlinear scales of the universe? Do we have a consistent picture of baryonic feedback effects? And can we measure dwarf galaxy masses to learn about dark matter? And of course, these are related. So in my talk, I'll introduce these science questions and why they're so exciting. I'll summarize how our key project, how our survey analyses work, and the main challenges that we face. And then I'll tell you that the work, what I really want to spend most of my time on is telling you about the work that my group is doing to tackle these challenges. So we have to devise new strategies. They are absolutely necessary so that we can handle the epic data that's about to start streaming in. And our standard analyses in these surveys are 2-point statistics, like the correlation function. And I get that's very much not trendy anymore. But whether we're doing a higher order statistics, wavelet, field level, deep learning, whatever you want, these challenges that we're tackling will be evident, and the strategies that we come up with will be needed, no matter what kind of statistic you're looking at. And finally, what I want to spend the end focusing on is that, you know, we can do a lot more than measure W or the dark energy parameter with a billion galaxies. And so I'll tell you about some of the new approaches the new ideas that we have for what we can do with this data. So taking a step back, what is weak lensing? If you think about it, we have a distribution of foreground massive objects, and they're spatially clustered. And their presence, their overdensities, distort the fabric of the universe, these gray blobs, so that as light from even further away background galaxies travels across the universe, their light path gets bent on the way due to these distortions. And as a result, we observe that the images of our background galaxies, they appear distorted, they are warped. And galaxies whose light travel past the same structures in the universe acquire coherent distortions, like these two on the left-hand side here. We observe them to be aligned, and that's the cosmic shear signal that we measure, these patterns on the sky in galaxies that are far away. putting these into context for the evolution of the universe, our weak lensing measurements, like clustering measurements, they measure the late time universe. So what we measure from the dark energy survey or from Rubin, we're really excellent at probing the late time universe, which looks a lot like the snippet on the right-hand side, which is a simulation from SLAC. So we're measuring the amplitude of mass fluctuations in the current epoch, so very large density fluctuations in a universe that is teeming with galaxies and has dark energy driven accelerated expansion. And these are very different from the measurements that we get from the cosmic microwave background. So they are measuring the imprint of very tiny density fluctuations when the early universe was just a hot, dense soup of particles. And this is a snippet, of course, from the Planck telescope, the Planck experiment, that delivered, this gold precision, this gold standard precision in cosmology. Now, what they measured is the density contrast of the universe as a function of scale, so the matter-power spectrum, and we'll keep coming back to this in this talk. And of course, we all know their measurements are an exquisite fit to this model. It is extremely hard to change the Planck CMB fits and measurements to want something different than our standard model. And what we do, the name of our game, is that we compare our weak lensing measurements to the Planck CMB, and we're really doing a very beautiful end-to-end test of lambda CDM. And we're saying, can we use the same picture that describes the seeds of our universe to fit the very large density contrast that we observe billions of layers later? And what we're trying to make up is a consistent picture of our universe. And really what we're seeing is a consistent picture. Mostly all of our cosmological observables are very well described by lambda CDM. And that should be deeply uncomfortable, considering that we don't really know anything about dark matter or dark energy. And so that's what we're really looking forward to using this new data for. Now, given that discomfort, I think it makes sense why our community gets really excited at the hint of any kind of tension. It's some clue of where to look, where our model is going wrong. And it's particularly intriguing because on the back of things like the Hubble constant, we see other discrepancies turning up in our measurements, so tensions. We're not quite level of discrepancies, hints of tensions, to varying degrees of significance depending on who you ask. So the S8 tension really is more of a persistent, annoying trend than any kind of discrepancy. These are the measurements that we get from our weak lensing surveys. S8 is the parameter that we can best measure. It is a combination of the amplitude of clustering and the amount of matter, the matter density. And so we always quote this S8 parameter as it's what we really measure well. And what we see is that none of our surveys measurements disagree with the Planck CMB to any real significance at all. But there is this annoying trend, and that's been true since 2013 with the first year PhD lens results. So I think kids alone claims 3 sigma, but the rest of us are somewhere like 2 sigma. And so what is this annoying thing? Well, in the last few years, really, it's kind of grown as being way more than a lensing thing. So since the start of my PhD, I've always heard, what are the weak lensers doing wrong? They just can't do anything with photometric data. Maybe one day it'll work. But in the last few years, we see all these other combinations of measurements, and I won't go into details of this plot, and I have a few issues of this plot, but there are other probes that are suggesting that maybe there are no S8 measurements coming from other ways of looking at the universe. Now, some of the science that I'm going to talk about is motivated by work that I did with George Staffiu. We stopped arguing about whether Planck was wrong or lensing was wrong and tried to put the pieces of the puzzle together. And very early on, we drew a plot like this and delved into the literature. We were like, what are all these low S8 results? And we tried to pick apart each analysis and find a pattern. And I'll come back to this, but the point I wanted to make here is that we're very used to the idea of testing lambda CDM over cosmic time. And the point that we wanted to highlight over the last few years is that it is as important to test lambda CDM over cosmic scales. So better than just making an S8 compilation, which can be extremely misleading because you're mixing all kinds of scales that you're looking at the universe on. It is better to place your measurements in a plot like this and think about what scales and what redshift is it probing in our universe. And that's the consistent picture that we need to have for a model. Now, the other question that I want to talk about is this baryonic feedback effects. So we can do a remarkable job at predicting the structure of a cold dark matter universe. And hydrosimulators, like some of you here, make increasingly more sophisticated hydrodynamical simulations that realize a vast range of galaxy properties and complex processes. AGN feedback is particularly important for weak lensing because it ejects baryons beyond the virial radius to the outskirts of galaxy groups and clusters, and the feedback redistributes the matter in the universe, resulting in a suppression of the matter power spectrum. So what I'm showing in this plot here is the ratio of the total matter power spectrum to dark matter only matter power spectrum. And you can see that the presence of baryons, they redistribute the matter so that you get this suppression as a function of scale, as a function of k scales, so small scales on the right and large scales on the left. Now, I will admit that I only got into this as a cosmologist, and now I'm more invested in the actual galaxy formation question. But the real reason we started here is because shopping around as a cosmologist, particularly a weak lenser where we measure nonlinear scales, we have to know how to model our nonlinear matter power spectrum. And there is really a large uncertainty on the amplitude and the scale extent of this effect that costs us a lot of precision in our analyses. And so really pinning this down is important for us going forward. And finally, what else can you do with 1 billion galaxies from LSST? Well, we really hope we can find lots of dwarf galaxies. So dwarf galaxies have a really relatively high dark matter content, few baryons. And so they're really a unique probe of dark matter on small scales and our understanding of the galaxy halo connection. Why don't we? What's the problem with them? Well, they have few stars, so finding them is really hard. And characterizing if they really are low mass galaxies or just distant galaxies is difficult unless you have spectra to tell you their stellar mass. If you could measure their halo mass, you could do many things. So you can constrain the low mass end of the stellar to halo mass relation. And as you can see, even in that purple regime, which is a bright dwarf, so the largest dwarfs, that regime still admits a wide range of theories of galaxy formation and dark matter theories. And so being able to pin that down would be amazing. And more than that, if you can measure the mass profile of the dark matter of the dwarf galaxies, so the mass as a function of the radius, that dark matter profile is extremely sensitive to different dark matter properties because they're so dark matter dominated, especially the inner regime. And so if we can measure that, we'd be able to say more about the nature of dark matter. And that's particularly true if you can push to even lower masses in that green shaded region. And so this has long been coveted, but it's extremely difficult to do without a tool like weak lensing, which gives you exactly that, the halo mass without caring about whether it's dark matter or baryons, and the mass profile. But to do weak lensing, you need a really large sample of dwarf galaxies. And so we really want to work on that and create a test bed for physics that impacts small scale cosmic structure. Now I'll change tact a little bit and tell you about the surveys that exist already before Rubin. So the Dark Energy Survey is the one that I'm primarily part of. I lead the main team in the Dark Energy Survey, and we really shine in area. It's the largest team and the largest area, 5,000 square degrees. And so compared to the other surveys, that's where we win. But the other surveys are equally as competitive, and that's because the Kilo Degree Survey, which is a European team, I did my PhD as part of that team, they have extremely brilliant wavelength coverage. So that means that they do an excellent job at characterizing how far away their galaxies are, which is really important. And HSC, which Bristolian and people more in this neck of the woods know, they are fantastic at being deep data. So they give you many more galaxies per square arc minute than you get in DES. And so these three surveys have really, they're state of the art right now, but they really are just training grounds in very different ways for what we can expect with Rubin or with any of the three coming surveys. Now, Rubin will blow us totally out of the water. So it's a 10-year survey, three-day cadence. Every 3 days, we'll keep building up a new image of our entire southern sky, getting us down to I-band magnitude of 27. And compared to DES, we will quadruple the area that we have and quadruple the number of galaxies that we get per square arc minute. So and very easy to imagine that in a couple of years, we will have 1 billion galaxies that we're doing. Now the camera is just beautiful. I got the chance to see it at Slack last summer. In their press release, brilliantly, they took pictures of broccoli to show how good the camera's doing, Romanesco broccoli. And it is remarkably now going on schedule. So it is set to fly out in a 747 to Santiago in the next couple of months. And then it will be driven to the top of La Serena, where, Cerro Patron, the one over from DES, to get ready for data. So the commissioning will start in the summer. I'll give you a quick flavor of how we do recleansing in our surveys. So on the cosmological scale, if you think about the box on the top right, we talked about it, just giving you a different view of it. If you think about the box on the top right, the background yellow galaxies travel through the large scale structure and their light path is distorted, and then we observe them to have to be lensed, acquire coherent alignments because of the lensing effect of the large scale structure that the light travels through. And so what we need to do recleansing from these galaxies is a measure of their shapes and a measure of their distances, how far away they are, so we know how much lensing they should have. Now, once we have those two pieces of information, we measure the correlation function. That's our standard in our analyses right now, as a function of angular separation, and we get statistics looking like this. To model that, we need to know how far away the galaxies are so that we can see how much lensing they would have. If we had spectra for every galaxy, that would be great, but it's way too expensive. And so what we do with just a photometric survey is we take our data and we bin them into redshift bins, and we estimate the redshift distribution, the probability distribution of redshifts for that bin of galaxies. So that's what you're looking at there, 4 bins. And you can directly relate the correlation functions to the underlying cosmology of the universe. And we're particularly sensitive to omega matter and sigma 8. And you can see that the thing that we constrain best is that S8 parameter. Just when in practice, that correlation function is just for 1 bin, but you have 4 bins, and you do the cross correlation and the autocorrelation, and you have 2 statistics, psi plus and psi minus. And so what you end up with is a very large data vector that we jointly fit all of these measurements to constrain cosmology. And I'll come back to this, but the blue regions are data that we currently throw away because we don't know how to model baryonic effects, which is a lot of data. Again, this is just a flyby to just give you a flavor of how this works in our large surveys. I love it. I think it's beautiful. When it works really well, but we have many sub-teams. It's very industry-like in a way, except that we don't all have a common employer. And so each of these bubbles kind of represents a team that works on their part of the analysis for a number of years. And we're moving from images on the left to cosmology on the right. There is much more that needs to be done on the data side, these blue parts, measuring the shapes and the distances and calibrating those. And then the orange kind of indicates the modeling parts. Now, as I said, that this is a challenging measurement to make, and I wanted to just highlight the 4 challenges before I get into how they're impacting us now. So on the data side, we have redshift calibration is challenging, and measuring the shapes is challenging. So the redshifts, this has been the most popular targets for lensing skeptics for the last decade. And this is what I spent most of my time on for the DES Year 3 analysis that we released a couple of years ago to try and make people more confident in what we were doing. So why is it so challenging and so scrutinized? The problem is that in our photometric surveys, we don't get these nice black lines, which would be spectra as a function of wavelength. And then in that scenario, you can very easily tell the difference between the type and the redshift of a galaxy, and they are degenerate. In reality, we just get observations for DES in R, I, and Z. And so you can see that for those 2 galaxies, it would be very easy to not know the difference between their redshift and type. And that is what the whole redshift problem is for us. It's characterizing that degeneracy and that relationship between a galaxy's wavelength or color and magnitude and their redshift. I won't talk about the shape measurement again in the talk, but our challenge there is just that we think we're measuring, people think we're measuring these very beautiful spirals, and really we're measuring fuzzy blobs that take up like 3 pixels on our images. And mostly each pixel has light coming from that galaxy, but also maybe a nearby galaxy, some galaxies behind it. And so characterizing which part of the light is coming from which galaxy is really difficult. Now on the modeling side, more recently people throw stones at these ones. These arise simply because galaxies are complicated. We like to think they're just ellipses in our analyses, but they can be intrinsically aligned, and that would just break the reclensing assumption that any alignment that you measure is due to cosmic shear, due to reclensing. So we have to carefully model that. And they have complex processes like AGN that redistribute the matter power spectrum on small scales that we need to be able to model. And so we need to make sure that our models are sufficiently flexible to not bias our results. And as a result, that means that we lose precision to account for those uncertainties. Now, how do these challenges stack up to each other now? Well, I made this part at the end of DES year 3, and we were trying to ask, but we have the largest data set, reclensing data set of all. How could we do better? How could we get better constraints on that S8 parameter? And so we're playing this game where we're just switching off uncertainties. So we're only looking at the change in the size of the constraints. If you switch off uncertainties, your constraints will be wrong. So we've just overlaid all the contours, but we're looking at how much smaller we can make them. And I wasn't sure if this was just really disturbing or I should be elated when we made this plot. But if you switch off your data uncertainties, so for every redshift bin, we have a redshift error and we have a shear error, how well we can measure the shapes. And if we switch those off, we do no better in DS, absolutely not much better. And this was really painful considering we spent 3 years, this is the side of the analysis that I worked on, painfully turning all these dials and trying to understand how we can accurately wrangle with this data. Maybe it's a good thing, which means that we sufficiently calibrated our data so that the uncertainties didn't dominate the power of our analysis. They were sufficiently calibrated. We weren't limited by observational systematics. Now, if you play the game on the modeling side, you pretend you perfectly know how to model intrinsic alignments, and you can use all the scales in your analysis. You can double your constraining power, at least. And so really, we are limited right now with DS, which is such a wide area survey and a shallow survey, we're limited by how well we can understand astrophysics. Now, that doesn't mean that you don't have to get the data stuff right. You can still be inaccurate, but they're not limiting our precision. That point is not easy to forget at Princeton. So this is a floor-to-ceiling picture of an LSST depth-like image. And so it's a daily reminder that we need to calibrate the shapes and the distances to all of these blobs that we can barely see in the next 2 years. But really, I wanted to just demonstrate quite how bad this problem is. And this is a lot of the work that's Justin Miles. So the way we do our reclensing, our redshift calibration for reclensing is we use a self-organizing map. We're not wedded to a self-organizing map, but we need a tool that helps us characterize this high-dimensional space of colors and magnitudes and can map to a smaller training sample, a spectroscopic sample where we know the redshifts. And so we use the SOM, we throw our DES galaxies into the SOM, and it defines types of galaxies. So in every cell, you have galaxies that look like each other in color and magnitude. And then you throw the spectroscopic sample, which is much smaller. We have 100 million DES galaxies and like 60,000 spectra or something. We throw the spectra in, and then every cell now has a redshift as well. And the biggest challenge, one of the biggest uncertainties that feeds into our analysis is due to that training sample. So spectroscopic galaxies, you have really accurate redshifts, but the problem is that they might not be representative. It might not be as complete a color space as our photometric sample, because we don't really have spectra for very far away galaxies or different colors of galaxies. And so to get around that in DS, what we do is we also use narrowband photometric data like Cosmos to fill in where we don't have spectra. And we defined an uncertainty due to that problematic training sample as the difference between the two. And that's the red bar on the right-hand side. So that's showing the error budget for each redshift bin, just due to redshift calibration. And the red bar is coming from our problems with the training sample that's not representative or not accurate enough. And you can see that it's growing with redshift, which is what's problematic, because with LSST, we're we're going to sufficiently deeper data that red bar is going to keep on blowing up. And hauntingly, the black line is the requirement for LSST year 10. That is where we need our total error budget to be. So not just the red, but all of them. And so you can see that we have a lot more work to do with understanding redshifts at the depth of LSST. So hopefully these challenges are clear, and now I'll tell you a little bit about our strategies. Clearly, we need novel and refined strategies. For DES, our year 6 analysis, our legacy analysis, which is ongoing, is our last stepping stone to try out these methods before Rubin. And we really think of Rubin as on the horizon for us. So this is a photo if you stand next to the DES telescope and look out at Rubin. It's one of those. So it really is on the horizon for us, and we're working with the idea that all the progress that we've made in DS lays the foundation going forward. And so my group's approach has been to use these current surveys to test out new strategies. And I was thinking about it, and almost all of our lensing problems, so the 3 that I'll talk about now, the main ones are missing data problems. And so what we're focusing on are getting the data or the measurements we need to understand these systematics, figuring out how to incorporate that additional data into our analysis, and also being creative on what we do if we don't get that data. What do we do if we still have missing information? How bad will our uncertainties be? So I'll talk about photodisease, IA, intrinsic alignments, and baryons. So this plot is just, it's not, don't think of it as real, it's just a demonstration. But this is to give you an idea of the type of plots that we looked at in this STOM. So as I said, you train with photometry and then you assign spectra to it. And what we look at is like how many spectra do we have for each type of galaxy, for each cell? And more importantly, what is the spread of redshifts for the spectra in that cell look like? So you want to have many spectra for each cell, and you want that sigma z to be really small, so that you're really characterizing a type of galaxy and its redshift very well. And this is kind of like what it looks like for DES on the 2 middle plots. And the right-hand plot is what we think it's going to look like for LSST year 10, just a demonstration. So we're going to have substantial amounts of color and magnitude space where we don't have training data. We have no way spectroscopically to know how far away our galaxies are, to calibrate those distances. And so what we've been doing is assessing the spectroscopic needs. So Justin Miles, who's a Princeton fellow at Princeton, and Jamie McCullough, who's a grad student at Stanford and moving to Princeton in the fall. We've been assessing our spectroscopic needs, making a case for the next generation spectroscopic surveys that they should maybe spend some of their time filling in these white areas for us. I'm trying to figure out strategies for what we do when we still have white areas, when we still have to do this kind of machine learning process where we don't have complete or representative training data. And I'll say that we're particularly appealing to DESI2, so the dark energy spectroscopic instruments. They have been rolling in redshifts for the last few years, particularly bright redshifts, not faint, not high redshift objects. But we are appealing to them that maybe they could just keep pointing at a patch of sky for us and get us some nice deep redshifts that we need. Now, intrinsic alignments, also just a missing information problem. We can't model this because we don't know what they look like. So people have been making for the last years direct intrinsic alignment measurements. So if you have an overlapping spectroscopic survey and an imaging survey, then you can make a data set where you know the shapes really well and you know the exact redshifts. And with that, you can do measurements to tell you how intrinsically aligned we expect our galaxy sample to be. And that's great, but typically those measurements have been for spectroscopic surveys where you have really bright red galaxies rather than faint blue galaxies like in our survey. And so we've been working on making these measurements in DESI, which will give us at least a bigger, it still won't solve the problem, but it will give us a bigger space. And we need to try to map, build a model that reflects how intrinsic alignments depend on these galaxy properties. Now we have the signal to noise to do that. And the challenge will be then building a forward model framework or something like that. This is what the bit that's still futuristic. Where we don't just take in for our bin of galaxies the redshift distribution, but where we can take in the color distribution, the luminosity distribution, the stellar mass distribution, and use that to inform more data-driven models. We really kind of once we get our redshifts, we throw away the fact that we know quite a lot about our galaxies, and we just use theoretical models with large uncertainties. But we can change that if we find a way to build more complicated models and analyses that take these galaxy properties into account. And finally, to say a little bit more about baryonic feedback. So this is work led by Leah Bigwood. Some of you in the Galaxy Formation group meeting today will have heard about this. I'll just give you a more concise version. We've been trying to figure out, how bad is this problem for weak lensing surveys? And so to start with, we wanted to test different models on the market and see how much they changed our cosmology results in simulated data and in our real DES-Y3 data. And so Leah's been considering 4 different models. So the DES approach is just to throw away all that data, but we've been using 3 more models. Halo model approach, which is called HM code. Now this approach is designed to be like a Halo model, but it is still calibrated to a simulation. So it's calibrated to Bahamas hydrosimulation. And so the model just has one free parameter, TAGM, that modulates how extreme the feedback is. We've been using SPK, which is a hydrosimulation approach. So the Antilles simulation, the same team as Bahamas and Flamingo, they built a suite of hydrosimulations and built an emulator from it that relates the baryon fraction to how much suppression you get, how strong feedback is. So again, it's more flexible than HM code in that it's not calibrated to one simulation, but still has one subgroup prescription. And our favorite model, a priori, our favorite model is baryonification. And we like this because it's flexible enough to not depend on any single simulation. And we think it can it's been shown to reproduce a range of hydrosimulations. And it has 7 free parameters. And I'm not going to go too much into, you should chat to Leah about the details of this, but what I wanted to make 2 points. One is that, so these are the 3 model spaces. One is that it's very easy to see that it's easy to change our main result, our S8 constraint, depending on how flexible you let feedback be. So for example, this is that HM code model, and they suggest, they recommend when you use their model, you use this prior, which brackets the Bahamas hydrosimulation. And so these are typically the results you get. But if you just lift the prior and let baryon feedback model be more extreme, you can very drastically change your S8 constraints because we probe nonlinear information. So our weak lensing data is, our S8 constraint from weak lensing is absolutely degenerate with how extreme feedback is. And that's true for baryonification and true for SPK. So one of our points is that we advocate that we really need to use more flexible models. We're in a bit of a dangerous regime if we pick one hydrosimulation and let that guide our primary cosmology result, given the uncertainty in these hydrosimulations. But the other point is that if you do that, if you rip open the prior space, then you have much larger S8 constraints. So you need to fold in additional observations to constrain those nuisance parameters. And so that's the second step of what Leah's been doing. She's been folding in kinetics and Yezodovich measurements into our cosmic share analysis for the first time in this kind of self-consistent way to constrain the feedback parameters. So KSE is the Compton scattering by moving plasma, and it generates a signal in the cosmic microwave background. It upscatters the CMB photons due to the bulk motion of the free electrons in galaxy groups and clusters. And it's linearly proportional to the electron number density. And we really like it because most of the hydrosimulations, or many of the hydrosimulations like Bahamas, are calibrated on X-ray data. And so by doing our analysis of cosmic share or weak lensing plus KSE, they are 2 very complementary ways of probing baryonic effects and constraining baryonic effects. And what we can see is, I just showed 4 of the results there. If we don't account for baryons, that would be wrong if you use all of the scales, and you get the gray constraint, which is quite low. If you use scale cuts like what DES does, you shift that up a bit, and you do some constraining power. And our approach is instead, you use the data, you use a flexible model, and you use something else to constrain the gas, and it's very easy, or it's much easier to get a high S8 value in that case. And I'll say more about this in a bit. But to wrap up the new strategies for delivering these data sets and these key projects in our surveys, I just wanted to flag, I won't talk about DES 6, but I lead the weak lensing group in DES, and I just wanted to highlight these 4 absolute superstars who've been kind of driving it so far. They're all graduate students, remarkably, and they've been making advancements in key aspects of our data and our modeling, and we hope to put out these results in the fall. I wanted to make sure I had enough time at the end to instead talk about new things that we can do with 1 billion galaxies. And so the first, to start that off, I'll talk about this S8 tension and our nonlinear solution that we think is the answer. So going back to this plot and referring again that this is work that started with George's staff unite when we tried to figure out what's going on here. And so we took each of our cosmological probes and kind of tried to think of the best one and fit together. How do they fit together? Where is this S8 information coming from? So to just walk you through this a little bit, you have Planck primary CMB in gray, and that is in tension with the weak lensing data in red and in blue. It's slightly higher in S8. The Planck, the CMB lensing is consistent with Planck primary, so you can combine them and get the yellow. And now CMB lensing is giving you a very different handle. It's giving you low redshift still at linear scales. So we're really starting to map out where in this plot is giving you a low S8 and where is not, and whether that's linear scales or not. And at the end of this, we tried to, what we decided was, we don't think this is early universe versus late universe, and we really need to change the conversation that's happening in the field to something that's instead, is this a tension between linear scales and nonlinear scales? Is it just nonlinear information that's saying you have a different S8? And that would be a very different puzzle to try to answer. And so this is the solution we proposed. And so how we got there is that after we delving into all of the different constraints in the literature, we played around with the lensing data, and we saw, number one, you could model all of the lensing data with a dark matter only power spectrum, pretend that baryons don't exist, like that gray constraint from Leah, and you get a really good fit. If you get a good chi-squared, you just get a very low S8. So there is this degeneracy where you can still get a low, you can still well describe your data without any baryons, but it has an impact on the value of the cosmology parameters that you get. There is just a clean degeneracy. You can also force the weak lensing data to agree with Planck lambda CDM, and you still get a good fit on large scales. And what you find is that you need to modulate the prediction on nonlinear scales, which is where most of our information is coming from. And so to demonstrate this, we reanalyzed the lensing data with this new model called AMOD, where it's the simplest thing you could write down. It just modulates the nonlinear matter power spectrum compared to the linear matter power spectrum. If that's something, change the nonlinear matter power spectrum. And if you do that and you look at the prediction of the dark matter power spectrum that you constrain compared to the true matter power spectrum, you see that in order to get the Planck CMB to reconcile with the weak lensing data, you need to suppress power on small scales. So this is the prediction you need for how much the matter power spectrum must be suppressed on small scales to solve the S8 tension. Now, as we've talked about already, other things suppress the matter power spectrum. That's exactly what baryons do. And so the first question is, is this exciting? Is this a smoking gun for non-standard dark matter? And the question is, we're absolutely not there yet. It could be that we just really don't understand galaxies. And so we put out this proposal and remained agnostic. It is either that this S8 tension, if you trust all of your data, the weak lensing data and the Planck data, it is either that the S8 tension can be sourced by some non-standard dark matter, or baryon feedback effects must be much more extreme than the simulations predict. And so you can see here that it's more extreme, for example, than these black lines, and even those black lines are widely ruled out in the galaxy formation world. So we summarized, we roped in one more, Calvin Preston jumped on board and produced those last constraints. And we advocated and encouraged that other analyses make sure that when they present their cosmology results, they consider that it's not just a high redshift, low redshift comparison, but a linear scale, non-linear. So you have to identify which scales you're constraining most in your cosmology analysis. And we went on to lay predictions for what we would expect from different probes if this hypothesis were true. So in this scenario, if A mod is the right answer, you need HSC cosmic share to come out low, and it did. You need ACT CMB lensing to predict an S8 parameter that's in agreement with Planck CMB lensing, and they did. And you need ACT CMB lensing cross correlations with galaxies to also come out consistent with Planck, because they would be even lower redshift, but on linear scales. And they did. And so far, so good. The most exciting updates will come from...
I did, and it was one of the scariest things I've ever...
I don't know how to turn that off.
No.
Okay. The most exciting update will come from DESI when they put out their VU and RSD constraints. They kind of sit at the lowest redshift and right at that gap right between linear and non-linear scales, and it will be a make or break for this idea. But we're really excited to see what they get and advocate that they identify where in K-space they're probing. But what we wanted to end with is that in this story is that weak lensing is the only probe that gives the opportunity to probe the full scale extent of our low redshift universe, and that is immense potential. And so it's wasteful when we condense all of that information into an S8 parameter. It's not capturing the power of this information. And so what Calvin's been working on now, and we've almost put out this paper maybe in a couple of weeks, is a new method that we should do our weak lensing analyses with. Forget constraining cosmology. We should just directly reconstruct the matter power spectrum with weak lensing data. And so Calvin's made a forecast for what we will get with LSSD desk year 10, and it will be beautiful, right? We have so many constraints that on the linear matter power spectrum to date, and with weak lensing, we can finally constrain the non-linear matter power spectrum on non-linear scales all the way to the linear scales, and that will be beautiful. Why is that so exciting? Beyond being able to compare with other probes on equal footing for each scale. But what we're most excited about is being able to test different non-standard theories that impact nonlinear scales. So we've been eyeing up and reading Keir Rogers' papers on axion dark matter models, and he's in the room. And they've made predictions, or teams of people have made predictions of how axion masses would change our nonlinear matter power spectrum. And with weak lensing data from LSST year 10, we should absolutely be able to weigh in on the masses of these particles and on constraints of these dark matter models. And that's really exciting. A couple more points. The final part of what Leah's been doing is that we wanted to reverse the story. We've been using our cosmic share data and worrying about baryonic effects, but you could just turn the problem upside down and use the cosmic share data and constrain baryonic effects. And what we found is really intriguing so far. So we've combined the lensing data with the KSC data, and we're constraining properties that are widely used to benchmark the hydrosimulation. So the matter power suppression, the baryon fraction as a function of mass, and the mass fractions. And the cosmic share data is shown in pink, and the combination with KSC is shown in purple. And what we see is that we need, so on the left-hand side, a far more extreme suppression than the baryon physics agrees. So that is satisfying the A-mod prediction without fixing to Planck or trying to solve the problem of what solves the S8 tension. We're just doing a cosmology analysis that frees astrophysics and cosmology parameters. If you look at the baryon fraction, the hatched line is the prediction from, or the measurement from X-ray data. And what we see is that we really want something lower than the X-ray data when you combine the share and the KSC. And that is interesting because so many of our hydrosimulations benchmark against the X-ray data. And so if that's not accurately describing a consistent picture of baryonic feedback effects, we're going to be in real trouble for our cosmic share analyses and other uses of the hydrosimulation. And on the last panel, we're looking at the mass fractions, and Leah's put some data on there and some predictions from the hydrosimulations, and again, our constraints are low. And so I'm excited to be able to talk more with the hydrosimulators here, like Paco and his team, and try to understand what we think is happening, and what is the tension that we're seeing now in galaxy formation effects. This feeds into work that Jameson Theory has been doing. He's a first-year grad student at Princeton. The same kind of tackling the same problem, but from a different angle. So now you can benchmark the hydro simulations by looking at the gas profiles as a function of halo mass. So we've talked about weak lensing in terms of cosmic shear, which is a shear-shear correlation. But the other measurement that you can make is correlating the background shears with a foreground lens. And weak lensing, when you do that, you measure the total mass around the halo, around the foreground lens. And so this is what weak lensing started out doing before we got to cosmic shear. By measuring this tangential pattern in the background galaxies, you get a handle on the mass enclosed around that foreground lens. So you can measure the mass profile of a foreground dark matter halo. And so that's what you get from your weak lensing measurement. This delta sigma kind of describes the mass enclosed in some radius r, and it gives you the total matter profile, the total mass profile. And James has been combining that with KSE measurements to get a handle on which part of that is coming from the gas. And with future measurements, you can build up a picture of how these gas profiles change as a function of halo mass when you jointly analyze with the weak lensing data. And the last thing I wanted to talk about was a little bit of change of what I usually do, kind of combining a few different worlds, and I'm really excited about it, is answering this question of can we work with dwarf galaxies to measure dwarf lensing? So I spent 3 years in a research actors group and learned a lot about dwarf galaxies. And one day she was like, we really want to be able to do dwarf lensing. And the problem is that we don't have big enough samples of data to do lensing with. You need large samples of data to be able to get a lensing signal, since the signal is so small. But they do have small spectroscopic surveys that get dwarf galaxies. And we were talking about it and telling her about the redshift work that Justin Miles and I were doing in DES at the time. And we were saying, we really are good at using large photometric surveys and small training samples to pull out subsets of our data according to some property. It's what we do for redshift calibration all the time. And so we use Justin's SOM framework to, instead of pulling out galaxies because of their redshift, so instead of using the combination of a large photometric and a small spectroscopic sample to pull out galaxies as a function of redshift, you can instead play that game and pull out galaxies as a function of their stellar mass, which you get from the spectroscopic data. We didn't know if it would work, but Joseph Thornton bravely took this on, not knowing if it would work as an undergraduate at Cambridge. And our results seem to say that it works really well, which we're very excited about. So this is the SOM now colored by stellar mass. And if we go into any of the cells, like the low mass cell, and look at the galaxies, just a random set of postage stamps, it is doing a good job of pulling out different types of galaxies that look like dwarf galaxies at least. And so we can use the SOM to define a low stellar mass sample that is much larger than what our spectroscopic data sets will give us in the next 10 years, and do lensing with that. So for this, we used a sample of 2,000 galaxies from the SAGA spectroscopic survey, and we pulled out that purple bin, a low mass sample from the photometric survey of 100,000 dwarf galaxies over the entire DES area. We measured their lensing signal, and we saw that there is a difference in our 3 stellar mass bins. So it really looks like this is a low mass sample. We modeled it using both just an analytic NFW on the inner scales, but our primary method is simulation-based inference. So modeling the entire mass profile. Remember that delta sigma describes the mass enclosed in a radius r. And from that inferred the halo mass. And we think that this is the lowest mass weak lensing measurement to date, just using public precursor data. And we're really excited about the prospects that we have going forward to be able to push this further. And what I mean, so Lena's jumped on board with the team to work on this, who's also a graduate student working at Princeton, a first year. And why we're so excited is because we already have data that will transform this. So we use 2,000 spectra from the SAGA survey, and we already have 100 times the number of spectra from the DESI survey of confirmed dwarf galaxies, and that's really the work of Elise, who is often here. We With LSST, we're going to have a much larger sample of photometric data. So our areal will grow by 4. Our number density will grow by 4. And with that deeper data, we'll be able to get even lower mass dwarfs, which are really baryon sensitive. And so we're really excited about the prospects of dwarf lensing going forward to constrain dark matter properties. Okay, I will leave you up with my summary and take any questions. Thank you.
Questions, please.
I think very nice results. So I think everything you said about lensing was based on the power spectrum, but just to comment that on small scales where you're looking at the baryonic effects, the field is very non-Gaussian. So I don't know if you looked at other things which.
We looked at other higher order statistics. No, so our approach has been, or at least the way that I've been thinking about it is, I know that the field is moving towards higher order field level, but the reality is for weak lensing data, we have enough problems at the 2-point level, as you can see. And so we're hoping that the things that we solve here will be able to inform the fancier analyses.
Sorry, the actual question was, if you take the model which has baryonic effects and solves the sigma A tension, are those models, have you checked if they're consistent with TSZ power spectrum?
That is, we have not done that, and that is something that we are thinking about. TSZ would be really interesting because it gives you a different view of different scales, and yeah, that is an exciting avenue that we want to go down. Yeah.
Other questions?
Yeah, here, go ahead, please.
Along those lines, when you use the KSZ, is it measuring the profile of the typical halo that is generating most of the feedback that you're seeing?
Yeah, good question. So we are using KSZ measurements, the high signal noise ones that exist from Emmanuel Chan, and they are of CMAS galaxies. So they measure the stacked KSZ profile around CMAS galaxies, which are LRG galaxies. Not representative of all of our galaxies. So in our model, we're careful to marginalize over a halo mass to make sure that we're not kin to that. But it is absolutely true that if baryon feedback looks drastically different for non-LRGs, we need more work and more measurements to be able to fill that in. We have some preliminary results on simulations that show that doesn't matter, that we're okay with that assumption. And they also show that it is really hard to fit this KSZ in our hydro simulations while also fitting the lensing. Something is there where it is doing something different to the feedback than what simulations usually prescribe.
Other questions?
Can you use the microphone?
Last one more.
Sure.
So I was just naive question. I was struck when you mentioned the photo Z degeneracy between a high redshift and a lower redshift. You used as an example an elliptical and an SPC.
Yeah.
Is there enough information in the image, the very few pixel image, that you could actually distinguish whether one type of galaxy or the other has a different redshift?
Yeah,
or
great
is this actually
question.
done usually for photo Z errors combined with the image?
We don't use anything other than colors and magnitudes. And like, for example, for the dwarfs, when we're looking for stellar masses, we take into account other information. For redshift calibration for our surveys, we don't. And I think that's absolutely the avenue that will change. So as I said, we're not wedded to a song. We just needed a tool to do this matching. But I think there are newer things on the market, especially things coming out of people at CCA where we can take spectra and match that to images. And I think that we will have more advanced methods to do this kind of calibration going forwards.
Is that the main source of error, different types of galaxies, or is it just a scatter?
For redshift calibration, the primary error as you go to higher redshifts is that red bar, which is the fact that we need better representative training data and more training data to beat that down. There are other sources of error, like on the method that we get from simulations or on the actual photometric calibration of our images, but they will be subdominant and they're worse under redshift. And they will be much less for LSST. But so really we're hitting this machine learning problem of we need a training set that to be able to map well to our full data set.
Other questions? Please, Sebastian.
Can you pull up the plot again where you were showing the comparison of different, like eliminating different errors in the weak lensing analysis and how that changed your cosmological contours?
Yeah. This one.
Yeah, that's the one, thanks. So you're showing here that when you turned off all these observational uncertainties, it had very small impact. And you said it was like a really notable result. Do you think that that's because all the observational uncertainties are well understood and they really have no impact on the cosmological result when you turn them off? Or is this a signal that they maybe are underestimated given that they have no impact on cosmology?
Yeah, good question. I should have been more clear. So they have no impact on the precision of our results, so not the accuracy. If you switch them off, you swing your results around. Or if you turn off our calibration effects, you get wrong results. So you absolutely must calibrate your data. So I mean, these values are important, not just the error on the Gaussian priors. So we're overlaying the contours here and only looking at the change in size. I don't think that we've underestimated our uncertainties though, because
this is the uncertainty on the uncertainties where you're trying
exactly.
to,
yeah.
Okay,
how much are we losing precision to this problem?
Oh, I understand. Okay.
It is not a solved problem because we have to get accurate estimates for our redshifts and our shapes, and that's a different question. But usually, we put quite generous errors on how well we think we've done our redshift and how well we think we've done our shape measurements. We were as generous as we could think to be. We doubled things when we didn't think we needed to double them. And so I think it's just, we have sufficiently calibrated it for this depth. I should also say that that's the point I was trying to make with the growing redshift with the red bars, that this is for DES. So out of all the surveys, we have this amazing area, but we're super shallow. And so we have the easiest problem with redshift calibration. We should be doing this really well. For LSST, we just don't have training data. We don't have enough spectra that are deep. And so these errors will be a lot bigger and they will impact. And for people who are familiar with the HSC analysis, it was evident there. They had large uncertainties in their redshift calibration and they had to lose tons of constraining power because of that.
Thanks.
Yeah.
Any final questions? Of squeezing one thing forward with people thinking. I'm curious, you had a lot of interesting approaches in terms of solution for redshifts that we don't have, and also for baryonic effects. So I'm curious of what you think about intrinsic alignments, because it seems very hard.
Yeah, so I think the first problem that we're trying to fill is that we need better observations. So you can't model something if you have no idea what it looks like. So as I was trying to say, but I said it too briefly, is that intrinsic alignments, we have direct measurements for spectroscopic surveys, which are typically big red galaxies like LRGs. And we see that they are very aligned, these types of galaxies. And so we make models based off of those. The problem is, or the difference is that in our weak lensing analysis, we are primarily blue galaxies that are very faint. And we've tried measuring intrinsic alignments for blue galaxies and never gotten a signal. So somehow blue galaxies don't align. And we don't have any measurements at high redshift, which is where we'll get LSST data. And so that is just a totally wide open space. So our approach that we're trying is to just get the direct measurements and start to build a picture of how they depend on galaxy properties. So at least we can extrapolate to where we don't have data, rather than just throwing this blanket theoretical model. And so the first step of that is where we've been splitting up the DES data in terms of the color of the galaxies and redoing the analysis. And the next step is to fold in other properties. Now, for the expertise that's here and they're complex in your bright ideas of thinking of machine learning or better ways to do analyses, what we need is some kind of way that we forward model, okay, this set of galaxies is this color, stellar mass, and luminosity, and so I'm going to analyze it in this way in my analysis. And building up that picture is a longer task, and I think it will be the way we do our analyses in the future.